So we have now basically left the planets of the solar system. Okay, we reached our last planet, which was in fact Neptune. But it was not always so, of course. At one time, we would have reached Pluto. But why is Pluto not considered a planet? Why did it get stripped of its thing? And now objects its size are called Plutoids. Well, there are actually several reasons for that. Okay. Number one is that um, Pluto is in a orbit. First of all, we always knew that its orbit was really weird. All the other ones were more or less on this elliptic, going around on this plane, going around the sun. Pluto's was always kind of more like a comet, where it kind of came in and then came back out again. Okay. And as we studied more and found more things out there, we found many objects out there that would also qualify as the same size or even bigger than Pluto. And if we're going to call Pluto a planet, then we're going to have all of a sudden about 20 or 30, 40, and the number keeps increasing, planets out here that didn't do it. But since these are more, if we've seen more about it, it is more like the asteroid belt that we saw earlier. And it's just areas where they have failed to form planets. And so this is called the Cooper, Kuiper, but it's pronounced Cooper belt. And this is where these are called Plutoids, these large objects. And it's basically where we think since they have failed to pull all this debris together to make a planet and cleared their orbital path of all this other stuff, like the other planets have, we're not going to consider them planets, okay? And so, anyhow, just for the record, this area is 30 to 50 astronomical units away from Neptune. Okay, so once again, we're going way far out there again. That's why it was so difficult to find Pluto in the first place, and means other objects. As we're getting more satellites going out there, as we have got better telescopes and different ways of seeing things, we have increased the number of objects that we found out there. And like I said, there's so many that after a while I said, no, these are not planets. They are just kind of like asteroids. Now, occasionally, some of these objects, especially if they're smaller than the Plutoids and the ones that are fairly good size. Some of the smaller ones get thrown out of orbit and can be pulled in. We think, like I said, for example, Triton, the moon of Neptune, might have been one of these larger ones that got pulled into its orbit. All right. But many of these objects will be, if they're lighter, will actually begin pulling toward the sun because of the gravitational pull of the sun. And as they go closer toward the sun, uh, they will rocky, ice-covered objects, but they begin to heat up as they become closer. And as they get closer to the sun, then they start having these tails or debris trails that are behind them as the ice either melts or little pieces of the rock and ice melt and break off. All right. And as they come through. All right. And these are what we call comets. And most of these comets that come from the Kuiper belt, and where the Plutoids are in that area, tend to come by within 200 years or less. Okay, so they come by fairly often. Halley's comets and some of these other comets that are predicted when they'll come back through are these type of comets. Okay, now if that comet goes through, usually the odds of them hitting Earth are not very good, but very often these tails are a lot longer. Okay, and so if they're if we go through, if Earth goes through the orbit of and hits that tail, which has all the little fragments on it, of course, then you have all these little pieces hitting the atmosphere, and we have meteor showers. And if we know when these comets are coming, there are certain meteor showers that can be predicted regularly because we know when we'll be passing through the tail of that comet. Okay, and so you see a lot of shooting stars or um, meteor showers kind of type things. All right. Now, if we keep going even farther than that, okay, we have what's called the Oort cloud, OORT. Okay, and these are really far out. No, I'm not flashing back to the 60s. Okay, I was only born in 68.5. Okay, but far out in this case literally means far out. They go from past the Kuiper belt, but they may be as far as 50,000 AUs or astronomical units, okay? Almost a fourth of the way to the next star. So we're talking about really far out there. And the are very far out, and because of that, for these comets to orbit, it may take thousands or even millions of years. So these are not going to be the short-term ones like the ones from the Oort cloud, which is at the edge of our solar system. What we think about our solar system, these are even farther out there, and so forth. Okay, and then, like I said, they can hit a planet. Like I said, once again, the meteorite that may have hit in the Gulf of Mexico and may have thrown up so much dust that it caused some mass extinctions or so. If that's what happened, that would be one that actually had a pretty good size one that had a direct hit. But like I said, if we pass through the tail of the comet, we just see meteor showers and stuff like that. We might have a few tiny meteorites that hit the ground from that, but usually not very much. Okay, so that gets us to the solar system. Now we're ready to go beyond that into the rest of the universe. All right. Now, as we have crossed away from the solar system, instead of measuring things in astronomical units compared to how close the Earth is to the sun, now we're talking about enormous distances. Okay, there's a whole lot of nothing. We have a Voyager that went into space in the 70s, and Voyager 1 or 2, I believe, and it's still going out there, although we're starting to have some issues with it. I think they can fix it, but we'll see. And it's still going. It's pretty much past the solar system as we know it, and it's still going out there. Hasn't got to any stars or anything like that. It's probably out in the middle of the area where the Oort cloud is right now. But anyhow, it's still going, which is pretty amazing considering how long ago it was sent up. But anyhow, we are now going to use light years. Okay, light years sounds like time. You're talking about years, but the light year is the distance that light can travel in a year. And you got to keep in mind that it's going about roughly 300 million meters per second. So um, that's pretty fast. So that's going to be about 10 trillion kilometers, if that helps you. Okay, but just keep in mind that'll be 1 times 10 to the 12th power kilometers. Okay, basically, just if you were at Neptune, which is the farthest planet, and you took the radius of that, that's only 1,000th of a light year. So it's going to be 1,000 times farther out than that. Okay. The Oort cloud is about 1.6 light years away. Okay. So light years are extremely long distances. We're talking about things that are extremely far from where we're at. Now, when we see stars, keep in mind that if that light from that star has been traveling at the speed of light, we are actually seeing light that had to have been released many years ago. Okay, maybe thousands, maybe millions of years ago, maybe even more than that. Okay, so it's almost like the light that we're seeing is like going back in time because when this light was given off, it was a long time ago. All right, all the stars we see, including our sun, which is our closest one, of course, um, is are in the Milky Way galaxy. Okay, we're not gonna worry about all the other different galaxies and stuff too much, but keep in mind when you see the stars or you see them in the sky, um, if you or follow them around, here's a time lapse photography. It looks as though they move in a circle in the during the night. But this, of course, is just like the sun's movement is really the Earth rotating on its axis, and so of course it makes them appear as if they were moving as well. Stars may also be in different positions because of where we are going around the sun. Different parts of the sun, Earth, we're going to be facing different stars in different directions at night. So there are changes in those. But they are on a regular basis. And probably old time civilizations understood more about the constellation or arrangement of stars than the average person is today, because we don't really use that as much as they built stories about it. That's why the constellations came up. They had shapes. Very creative imaginations if you look at some of the shapes and what they said it was, but that's okay. And they were trying to explain the world around them doing that. But they were probably much more aware of the stars and the constellations and how that worked than we are. Now, when we look up in the star, we see stars. There's two things we want to talk about. There's the apparent brightness and there's luminosity. Okay. Um, Apparent brightness is just what seems to be the brightest star when we look up there. Okay. However, it may not be as bright a star. It may be giving off less light, but it might be closer to us, and so it looks brighter to us. So the apparent brightness is how bright it appears to be from Earth. Luminosity has to do with the actual amount of light given off by uh, a star. Okay, and so um, brightness operates on the inverse square law, kind of like gravity and a bunch of other things we talked about. Uh, in other words, if you double the distance, it only looks 1/4 as bright. Okay, and exponentially decreases as the distance increases by a half. Then you see 1/4 as much brightness and so forth. So the distance can make a big difference. A closer star, even though it's not as bright, may look equally bright or more so to us. Now, one of the other characteristics you may notice, especially as you look through here, is you see the different colors of star, and color is primarily a function of temperature. Okay, and kind of like a bunch of burner flame, blue is the greatest temperature, followed by yellow and then red. Okay, and so if you want the hottest, they're going to be the blue stars, then followed by yellow, and then followed by red. Um, Now, we're going to talk later about red giants. Someone says, well, but if they're not as hot, not as high, much temperature, why do we see them? Well, they're extremely large, and because of their largeness, that makes them perhaps easier to see at times. Okay, but the temperature is going to be lower in a red star, say, than a blue star. All right. Now, we going to talk about the HR diagram, which stands for Hertzsprung Russell, which are the two gentlemen who developed that. But we call it the HR diagram because Hertzsprung Russell is just a little too much to say, okay? And so on this diagram, it's just a way to organize what we know about stars and where they are, okay? As you go up here, they're brighter and brighter. Okay, so the brightness increases as you go up here, but their temperature increases as you go this direction or to the left, which seems kind of counterintuitive. Most graphs get bigger as you go to the right, but in this case, it does that. Why do they do that? I don't know. Maybe they like the slant better that direction. You just have to ask them. I'm sure there's a good reason. I don't know what it is. All right. So um, basically, um, the main sequence stars, these are ones that are just going through normal nuclear fusion where we're going hydrogens being fused together, right, to make helium. All right, and then based on their size, okay, the sun is kind of down here below medium size, okay, and they start up here and then work their way down to there. That is where most stars fall. But then they have these supergiants and giants, red giants and supergiants over here. What do we have with all these stars? And we have some down over here. They're called white dwarfs, kind of down over here. Okay, and so and they're actually hot. White is hotter than blue, generally speaking. Okay, we didn't talk about blue or white when we're talking about temperature. It's actually high. But they're down over here where they're not very luminous. Okay, so what's going on here? And basically, as they tried to explain this, this is where they kind of came up with the life cycle of a star. Now, obviously, we think our sun formed 5 billion years ago. We think it'll be another 5 billion years before it burns out. Okay, so you and I are pretty safe. We're not going to have to worry about that. Okay, the upcoming elections, yeah, that might be an issue, but the sun burning out is probably not a big issue. We really need to spend a lot of time sweating. Okay, so if no one's been around long enough to see the life cycle of a star, how do we know? Well, we're looking at the stars we do see and uh, and trying to put them in order of what we think happens as they go through this life cycle and explain why a lot of these different stars are where they are on the Hertzsprung or H.R. Russell diagram. Okay, but I know I've just built up your enthusiasm for that, and you're on the edge of your seat, but you're going to have to wait till the next lecture to find that out. Okay, all right, see you in a bit.